Okay, so this will be an introduction to organic chemistry, hydrocarbons, what exactly are hydrocarbons. Okay, so what is organic chemistry? It is the branch of chemistry that focuses on studying the compounds that are majorly made up of carbons. Okay, where do you find hydrocarbons? Most of our compounds in our body, sugar, glucose, all of those other compounds in our body like proteins, all of those are based up of organic compounds. Oils, all the oils that we consume, they are basically an example of organic compound. And why are they called organic specifically? So initially scientists used to think that organic compounds are the compounds that are made by organisms, okay, that cannot be chemically synthesized. Those are the compounds that are prepared by animals, that animals synthesize themselves in their body. So they called it organic. Okay, but now we know that since we have developed so many techniques, we know we can definitely synthesize some of these organic compounds directly in labs without taking help from an actual organism. Okay, so by definition, what are organic compounds? These are the organic chemistry is the study of carbon containing compounds. Okay, some of those exceptions include, like if we talk about CO2, carbon monoxide, carbon dioxide, carbonate, cyanate, some of those carbon containing compounds you guys have already seen previously, but those are regarded as inorganic compounds. Okay, so what we were studying up until now was all inorganic chemistry. So there the focus is basically on all the other elements in the periodic table other than the carbon containing compounds. Okay, so here are some of the properties that differentiate organic compounds and inorganic compounds. For instance, when we talk about organic compounds, they majorly are composed of carbon and hydrogens. Sometimes you will see they consist of other elements like oxygen, sulfur, nitrogen, phosphorus. There are some halogens like chlorine, fluorine, bromine, iodine, but majorly it is carbon and hydrogens. Okay, whereas when we talk about inorganic compound, that consists of everything else that you see in periodic table, metals, non-metals, everything. Okay, these organic compounds majorly form molecules, whereas the inorganic compounds usually consist of ions, like we have seen when we talk about metals and non-metals. They are ionic compounds, right? So they consist of ionic bonds. Some of them we saw do have covalent bonds, right, like molecular compounds, but most of them are usually ionic. In case of organic compounds, the type of bond that you are going to see that makes the sharing of electrons, that are formed by sharing of electrons, which is mostly a covalent bond. Okay, so only bonds that you would see in organic compounds are basically going to be covalent. There are no ionic bonds here. In case of organic compounds, you will see that most of the organic compounds are non-polar. Most of them are non-polar. There are some compounds that become slightly polar depending on if there are some electronegative atoms in that group. For instance, if you see any oxygen there, if you see any nitrogen in the compound, that might make that compound slightly polar, but most of them are non-polar. And in case of inorganic, you saw most of the compounds, for instance, if they're ionic, they are polar, and some of the compounds can be non-polar, but most of the compounds can be polar if they are ionic, and they could be polar covalent or non-polar covalent. That is something we already saw before. Okay, now the next few properties are their melting points and their boiling points. Organic compounds usually have very low melting and very low boiling points. Okay, so most of the times you will see these organic compounds boil very easily or they melt very easily. Okay, for instance, oils. Like I said, oil is an example of organic compound. So if you see oils, most of the oils exist as liquids, right? Sunflower oil, vegetable oil, all those oils most of the time exist as liquid, meaning they are already melted. You don't see those oils in solid form, correct? So that means they have a very low melting point, whereas in case of inorganic compounds, they usually have a very high melting and boiling point. Why? Because they have much stronger force of attraction keeping them together, right? Whereas in case of organic compounds, they're usually non-polar. So you know, in case of non-polar compounds, most times the force of attraction between non-polar compound is dispersion forces, right? So they have less intermolecular forces within themselves. Therefore, these compounds have usually lower melting and boiling points. Okay. On the other hand, these compounds are highly flammable. Okay. For instance, acetone, ethanol, all kind of alcohols, ethanol, methanol, all those things are very highly flammable. They are all organic compounds. Okay. Whereas in case of inorganic compounds, they are not that highly flammable. Okay. Next, we come to solubility in water. Now, if or as organic compounds we know are very non-polar, that means they are usually not soluble in water, right? Because water is a polar compound. If you guys remember, we talked about like dissolves like. So polar compound will dissolve in polar compounds. So water is a polar compound, but most of the organic compounds are non-polar. Therefore, non-polar compounds do not like to mix with water. Example, again, you can just simply think of oil. Oil and water, they don't mix together. Whereas most of the inorganic compounds are soluble, but some of those can be insoluble as well. For instance, we saw lead chloride, silver chloride, all those compounds, right? But most of them are usually soluble in water. Okay, so those are some of the properties that you can see are different in case of organic compounds and inorganic compounds. Okay, any questions? So organic compounds basically will be made up of carbon and hydrogen atoms, and we saw it might contain some other non-metals, oxygen, sulfur, nitrogen, phosphorus, halogens sometimes. Okay, where are these organic compounds usually found? Basically everything, mostly everything. Gas, gasoline, petrol, medicines, most of the pharmaceutical products are usually organic compounds. Shampoos, detergents, most of those are organic compounds. Plastic, clothes, like synthetic clothes that we wear, nylon, again, that is an example of organic compound. Perfumes, oils, all of those are example of organic compounds. Okay. Usually in case of organic compound, how can you identify if it's an organic compound? The formula is usually written by carbon first, followed by hydrogen, and then if the formula essentially is similar approach, like you write the carbon and the subscript, let's say if I write here N, this subscript tells you the number of atoms. Hydrogen, let's say this is 2N, this tells you how many number of atoms of hydrogen there are. So usually we start the formula with carbon, followed by hydrogen, and then if there is any oxygen or phosphorus or halogens, they usually follow afterwards. Okay. Properties, we already talked about most of these properties. So they have covalent bonds, they have low melting and boiling points, they are highly flammable, and they are not soluble in water, which means they don't mix with water. Okay. Okay, now we'll talk about what are different types of hydrocarbons. Okay, these organic compounds sometimes are referred to as hydrocarbons. Okay, so first type of compound we'll talk about are hydrocarbons. The name tells you it consists of hydro and carbon. Hydro here means hydrogen, and carbon here is coming from carbon. So these compounds will consist of only carbon and hydrogen. So hydrocarbons are the compounds that consist of only carbon and hydrogen. No other non-metal is present here. Okay. Hydrocarbons can be of 4 different types. Okay, for you guys, what you're going to see is the first one is called the alkane. Okay, so there will be a lot of terminology, a lot of naming here, which you kind of would have to memorize. So the first kind of hydrocarbon is alkanes. Then we have alkenes. So what difference you see here is essentially in this alphabet in the middle. That's it. Alkane, alkene, alkyne. And the last is aromatic compounds. Okay, so what are alkanes? Alkanes are essentially compounds which consist of carbon. All the carbon atoms here have only single bonds within each other. Okay, so let me actually draw again something right here. So you could also try to categorize it like this. So hydrocarbons can be 2 types. One is saturated, major classification. One is saturated, the other one is unsaturated. What does saturated and unsaturated mean? Saturated means all the bonds that are present between carbon here are all single bonds. Okay, so carbon atoms here will always consist of single bonds. That is saturated hydrocarbon. Unsaturated hydrocarbons are the hydrocarbons where carbon atoms could have a double bond within each other, or they could have a triple bond, but there has to be at least one double bond or a triple bond. Okay, those are unsaturated. The saturated hydrocarbons are called alkanes, and the unsaturated hydrocarbon, we could divide it further into three classes, which is alkene, alkyne, and last is aromatic, that you're seeing right here. So alkene, alkyne, and aromatic. Okay, what are alkenes? Alkenes will always consist of at least one double bond between two carbon atoms, at least one double bond. Alkynes will consist of at least one triple bond between two carbon atoms. And aromatic compounds will consist of at least one benzene ring. And what is benzene? We'll talk about that later on, but basically it will look something like this. It's a ring structure, 6 carbon ring structure. We'll talk about that later on, but basically this is how you could classify hydrocarbons. Okay, there is saturated and unsaturated. Saturated is alkane, unsaturated is alkene, alkyne, or aromatic. All right. Okay, now another very important thing before we begin with anything else is that carbon atom, how many bonds can a carbon atom form? 4 maximum. It belongs to group number 4. So each carbon, in order to have its octet rule completed, right? In order to have 8 electrons in its outermost orbit, it has to form 4 bonds. These 4 bonds can be formed with same compound, same atom, like X, 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 or it could be completely different, X, Y, Z, or let's say A. It really doesn't matter. Okay, these 4 bonds could be with one or different types of atoms, but it has to have 4 bonds. Unless it has 4 bonds, the carbon is not satisfied and your molecule is not stable. Okay, in organic chemistry, every carbon has to have 4 bonds. Okay. All right, so now let's keep on going with our alkanes. Alkane, the general formula for an alkane is CnH2n plus 2. Here N is the number of carbon atoms that are present in a molecule. For instance, if I ask you what is the smallest alkane that is possible, smallest alkane would be which would have only one carbon atom, right? So one carbon atom means our N is 1. So what would be the actual formula? If N is 1, hydrogen will be 2N plus 2, which is 2 times 1 plus 2, which would be 2 plus 2, so 4. So the formula is going to be essentially CH4. Okay. How about carbon? If it is 2 carbons, if N is 2, what would be the formula? N would be 2, so C2H, 2N plus 2 would give you 2, perfect, 6. 2 times 2 plus 2, 6. So the formula would be C2H6. So you can basically come up with formula for an alkane if you know the number of carbon atoms. Okay. So this is the general formula, CnH2n plus 2. Okay. For instance, the simplest alkane is 1 carbon, which is methane. This is called methane. This is the natural gas that is consumed in our houses, gas stove that we usually have at our house. The gas that is supplied there is methane. The next, the 2 carbon alkane is C2H6, which is called ethane. It is basically also one of a very tiny component of the natural gas. Okay. Lastly, we have not lastly, but if you have a 3 carbon, what would be the formula? 3 carbon is going to be C3H8. How do you get 8? Again, 2 times 3 plus 2, which would give you 8 carbon atoms, right? So, 8 hydrogen atoms. So that is called propane. This is also one of the fuels. So you'll see that most of the alkanes actually are used as fuels. Okay, and we'll talk about that eventually. Now we'll talk about how do you actually name these compounds. Okay, for naming organic compounds, we usually follow the system which is given by IUPAC. IUPAC is the International Union of Pure and Applied Chemistry. So IUPAC has a system, has certain rules, so that the compounds are given the same name followed by the same rule throughout the world. Okay, so most of the names that you're going to see naming in organic chemistry is given by IUPAC system. Okay, how do you name alkanes? You see this at the end, ANE. Whenever you name alkane, you would see their name will always end with ANE. Okay, for instance, we saw methane, ANE, ethane, ANE, propane, ANE. Right? So their names are always going to end with ANE. And what is the prefix that is used in front? The prefix that is used in front of ANE tells you the number of carbon atoms that are present. Okay? What do I mean by that? These are the prefixes that are used. So for instance, if it is one carbon atom, the prefix is meth. Always in chemistry, if it is one carbon atom, the prefix is meth. And these are the prefixes that you would have to memorize, because this will continue throughout the rest of this whole course. Okay. If it is 2 carbon atoms, it is eth. If it is 3 carbon atom, it is prop. If it is 4 carbon atom, it is but. These are the tricky ones which you might have never heard. You might have not heard of these before, but the rest are fairly easy. For instance, 5 is pent. These are basically the names that are given to the polygons, right? 5 corner polygon is called a pentagon. So that is coming from pent. 6 carbon is hex. 7 carbon would be hept. 8 carbon would be oct. 9 carbon would be non. And 10 carbon would be dec. Okay, so these are the prefixes that are used for number of carbon atom. Depending on what hydrocarbon or what compound we are talking about, we could change if we could add any suffix to these prefixes. The suffix keeps on changing, the prefix stays the same. Okay, for instance, if we are talking about alkane, which is 1 carbon, it will be methane. Alkane with 2 carbons, ethane or ethane. Alkane with 3 carbons, propane. Alkane with 4 carbons, butane. So essentially everything will end with ane, and the prefix would be the number of carbon atoms. Okay, so meth, eth, prop, but, pent, hex, hept, oct, non, and dec is something that you should definitely memorize. Okay, so these are the first 10 alkanes. If you want to write their formula, simplest question could be, what would be the formula for a hexane molecule? What would be the formula? You know, hexane has 6 carbon atoms. So hex is a prefix for 6. So it would be C6. And what was the formula? It was CnH2n plus 2. So it would be C6H14. Perfect. So n here is 6. So 2n plus 2 would give you 14. So you could, if you know the name of the alkane, you could come up with their molecular formula. Okay. The next thing we'll talk about is how do you write these chemical formula of these compounds. One is, you saw here, we write their molecular formula, which is just how any other molecular formula is written. You write carbon, and a subscript, which tells you number of atoms of carbon, hydrogen, number of atoms of hydrogen. There is also a couple other ways usually you will see formulas written in organic chemistry. One of those is called a condensed structural formula. So we'll talk about that. And the third one is called a line angle structural formula. So you could write methane like ethane, all these molecules like this, or in this form, or in this form. Okay, these all represent the same molecule. How do you write these formulas? For instance, if I were to draw the structure of methane, what would be the actual expanded structure for methane? Methane is CH4. So we have one carbon, carbons are always written in the middle, and then we have 4 hydrogen atoms attached to it. Right? So one carbon, 4 bonds, and each carbon has to have 4 bonds. So that would be the formula for methane. Let's write the chemical formula or the structural formula for ethane. Ethane has 2 carbons. Always join the carbons together by a bond first. So this has 2 carbons, so we'll first draw 2 carbons bonded to each other by a single bond. Okay, and now you know that each carbon has to have 4 bonds. So this is 1, 2, 3, 4, 1, 2, 3, 4, and each of them, if it is a hydrocarbon, the only atom you would attach here is hydrogen. So you attach hydrogens right here. So what is the formula now? C2H 1, 2, 3, 4, 5, 6. So that gives you the formula for ethane. Okay, and what is this? This is called an expanded structure. Okay, this is expanded structure. And this, what we wrote here, C2H6, is the molecular formula. You could also call it expanded structure or expanded formula. Okay, now let's see how can I convert this expanded formula into a condensed formula. What is a condensed formula? In case of a condensed formula, you do not show any of these carbon-hydrogen bonds. Okay, so you do show the carbon-carbon bonds, but you do not show any carbon-hydrogen bonds. So what you can do is you will show this carbon right here, which is carbon 1. How many hydrogen does it have? 1, 2, 3. So it will be carbon followed by 3 hydrogens. And this carbon is bonded to the next carbon, which is right here. How many hydrogen does it have? 1, 2, 3. So H3. This is a condensed structural formula where you do show carbon-carbon bonds, but you do not show any carbon-hydrogen bonds. Okay? Here, another important thing is sometimes students get confused here that if you write CH3, bond CH3, you see the bond here seems like it is between hydrogen and carbon. But remember, this bond is between 2 carbon atoms. Okay, even though we write it like this, because remember the first thing we discussed was that when you write the formula, you write carbon first followed by hydrogen. So that's why you would see the bond in between here, but this bond is actually between 2 carbons. Okay, perfect. And what is the line angle formula? Basically, line means you simply draw lines. Each corner of the line represents 1 carbon. Okay, so in the line structure formula, we do not show carbons, we do not show hydrogens. Only thing you will see is lines. If there is any other atom like oxygen, nitrogen, hydrogen, sorry, not hydrogen, halogens, those would be shown, but carbons and hydrogens are never shown in a line structure. Okay, so for instance, if I draw this single line, how many corners does this have? It has 1 corner right here. So this is 1 carbon, the second corner is right here, so this is second carbon. And now it is showing me this single bond, which means there is 1 single bond between these 2 carbons. And we know as organic chemists that each carbon has to have 4 bonds. So by yourself, automatically you're going to draw 4 bonds and you would draw hydrogens. If nothing else is given, that means it is carbon is bonded to hydrogen. So again, the formula comes out to be C2H6. Okay, so even though somebody would draw this as a structure, a single line, an organic chemist would know that this is ethane. Okay, let's try some other molecule. I'll erase this. Let's move on to the next carbon, for instance, propane. Okay, if I ask you, okay, we have a molecule of propane, can you write the molecular formula, expanded structure, condensed structure, line formula for propane? Okay, so how would we do that? Propane means, first thing you see is, it's an ane, meaning it's alkane. So it is a saturated carbon, hydrocarbon. Prop means 3 carbons. So what would be the molecular formula? C3, and again, I'll write it right here, H2N plus 2. So it would be C3H, 2 times 3 is 6, plus 2, 8, C3H8. So that's the molecular formula. How do we write the expanded structure? Expanded formula would be 3 carbons, so 1, 2, 3 carbons. Let me draw it here. Expanded needs more space. 1, 2, 3 carbons. And each carbon has to have 4 bonds. So this carbon has 1 already, 2, 3, 4. This carbon in the middle has 1, 2 already. So 3, 4. This carbon has 1 already. So it would be 1. 1 is here. So 2, 3, 4. And now to each of these bonds that we drew, we will add 1 hydrogen. Right, and now you can confirm your structure. This is 1, 2, 3, 3 carbons. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8. So your final structure is C3H8. Okay, next let's draw its condensed structure. How would the condensed structure look like? Condensed structure would be, you only show carbon. First carbon has how many hydrogens? 1, 2, 3. So this is CH3. Single bond, the second carbon, which is how many hydrogen? 1, 2. So this will be CH2. Then another bond, which is third carbon, number of hydrogen is 1, 2, 3. So this would be CH3. So this is again a structure for propane. This is the condensed structure for propane. And if we were to draw its line structure, how would it look like? We will draw zigzag lines now. Okay, because we need to draw 3 corners. So I start from here. This is carbon number. Okay, so we were right here. This was CH3, CH2, CH3. This was propane, right? We are drawing the line structure. So I start with one corner, which is right here, carbon number 1. I draw one line. I draw the second corner, which is right here. Then we move on to next corner. So each corner here is a carbon atom. So this is 1, 2, 3. So this you have drawn 3 carbons. Since it's single bond, it means you have drawn an alkane and will satisfy each of the carbon with hydrogens. Okay, so if you are given a line structure, you should be able to go from line structure to its actual formula. Alright, how would we draw butane? Drawing the line structures is easiest when you're working with hydrocarbons. Hydrocarbons can be, for instance, you're seeing right here, this is only 10 carbons. Sometimes organic compounds can be 20 carbons, 30 carbons. So what do we do in that case? It's easiest to write these structures in that case. That's why we do line structure. So if I were to draw butane, how would I draw butane? Butane would be, I start from a corner, I draw, this is carbon number 1, I draw 2, 3, I go 2, 3, 4. So this is 1, 2, 3, 4. Total number of carbon here is 4. So this is butane. Okay, if I were to draw, let's say decane. Decane is how many carbons? 10 carbons. So how would I draw the structure for this? It would be 1 is right here, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can count that the number of corners should be 10 now because it is 10 carbons. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That basically represents a structure of decane. Okay, and now if I ask you, I give you the structure and I ask you, can you draw the condensed structure for this? How would you draw this? Or expand it? You should know that this is the carbon number 1. Then I have 2, 3, 4, 5, 6, 7, 8. I'll just draw them right here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you know that each carbon has to have 4 bonds. So I draw 4 bonds for this. This already has 2 bonds, so 1 more and 1 more. This has 2 bonds, so 1 and 2 more. This has 2 bonds, so 1 and 2 more. This has 2, so 1 and 2. Okay, and you can keep on adding hydrogens to each of those. Make sense? Or the other way would be, if you really don't want to do the expanded structure, you simply add hydrogens instead of 1. So this carbon already has 1 bond. How many more bonds does it need to be? 4, 3 more. So which means how many hydrogen does this have? 3. This already has 2 bonds. How many more hydrogen does it need? 2. Same thing here. This needs 2 more, 2 more, 2 more, 2, 2, 2, 2. And finally, this carbon has only 1 bond, so it needs 3 more. So that is how you could know that this structure actually represents this molecule. Okay, does this make sense? So these are all different types of structures that you might commonly see now in rest of this organic chemistry. Okay. All right, so next few slides are basically explaining you again everything what I just explained to you. So what is molecular formula, what is line angle formula, what is expanded formula. Okay. All right. So next thing we'll talk about is right here. Given the following, let's try this question. Given the following expanded structural formula, provide the molecular formula of this compound. So what would be the molecular formula of this compound? Molecular formula is easy. You just write carbon, number of carbon atoms, hydrogen, number of hydrogen atoms, right? So what is the number of carbon atoms here? 1, 2, 3, 4, 5. Hydrogen is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is total number of 12 hydrogen. Next is asking condensed structural formula. Condensed means you do not show carbon-hydrogen bonds. So we'll write carbon. How many hydrogen does this have? 1, 2, 3. So it would be H3. Then a single bond with the next carbon, which is right here. How many hydrogen does this have? 1 and 2, so hydrogen 2. Next I draw this single bond right here with the next carbon. Again this also has 2 hydrogen. The next is right here which also has 2 hydrogen atoms. And finally we have carbon number, last carbon, which has 1, 2 and 3 hydrogen atoms. So this would be our condensed structural formula. It is 1, 2, 3, 4, 5 carbons. Okay. Lastly, we have the compound name. So what would be the name of this compound? So first thing you see here is that this is all saturated. This has all single bonds, meaning this is an example of an alkane. Which kind of alkane? 1, 2, 3, 4, 5. 5 carbon is pentane. So the name is going to be pentane. All right. Okay, so now can you guys do this? Write the condensed structural formula for ethane. Always remember, whenever name is given to you and you are asked for the formula, you always start from the end. Okay, always start from the end. So in this case, ethane means it is starting with, ending with ane. So I know this is alkane. Alkane means all single bonds between carbons. Eth means number of carbon atom is 2. So we draw 1, 2 carbon atoms. Now we simply satisfy these carbons with adding hydrogens. Okay. So the question is asking condense. So we'll simply write down how many hydrogen atoms. So this carbon already has how many bonds? 1. How many hydrogen does it need to be satisfied? The first carbon would need 3, right? This carbon already has 1 bond. It needs a total of 4 bonds, which means it needs 3 hydrogen atoms. Same is true for this. It needs 3 more hydrogen atoms. So your condensed formula would be CH3, CH3. Okay, this is asking condensed. Don't give the molecular formula. Okay, it's asking condensed formula. Okay, next is heptane. Again, this is ane, which means all single bonds. Hept means how many carbon atoms? 7. Hept is a prefix for 7 carbon atoms. So you simply draw 7 carbons, 1, 2, 3, 4, 5, 6 and 7. All of those carbons should have single bond because it's alkane. Now we fill up the octet with hydrogens. So how many carbon, this particular carbon, how many bond does this already have? 1. How many more does it need? 3 more. Every carbon has to have 4 bonds. So we will add 3 more hydrogens. How about this carbon? This carbon already has 2 bonds, which means it needs how many more bonds? 2 more. So hydrogen number would be 2. Next carbon, this also has 2 bonds already, which means it needs another 2 bonds, so 2 more hydrogen atoms. The next carbon, this also has 2 bonds already, it needs 2 more bonds, so 2 more hydrogen atoms. The following carbon also needs 2 more. The next carbon also has 2, needs 2 more. The next carbon only has one bond yet, so it needs 3 more bonds, so we will add 3 more hydrogen atoms. Alright, so this is the condensed structure for heptane. So if name is given to you, how can you go to structure? This is how, these are the steps you would follow to find the structure of the molecule. Alright. Okay, next we'll talk about a different type of alkane, which is called a cycloalkane. So cycloalkanes basically are cyclic molecules. Cyclic means they are ring structures. Ring structures. So in these molecules you would see something drawn like rings. So for instance like this, everything will be joined to each other. All carbons will be somehow connected. For instance like this. For instance, these are examples of some cycloalkane or cyclic structure. You see right here, this is a ring structure now. This right here at the bottom is a ring structure. This right here is also a ring structure where all of them are basically forming a ring. They are connected to each other somehow. These are called cyclic structure. If these have all bonds, again, if all the bonds are single bonds, they are called cycloalkanes. Okay, how do you name them? The naming is very simple for cycloalkane. You basically write the name of the alkane first. If it was a straight chain alkane, you write its name and then put a prefix in front of it, which is cyclo. Okay, so for instance, if we were to name this particular compound, how would you name this? How many carbon atoms does this have? Right here, this has 1, 2, 3. Total of number of carbon atoms is 3. What is the name for the alkane with 3 carbon atoms? Propane. You simply put a cyclo in front of it, so this becomes cyclopropane. Okay, how about this right here? This is how many carbons? 1, 2, 3, 4. 4 carbon atoms. So this is, usually it would be called butane, but because this is cyclic, it will be called cyclobutane. Okay, how about this right here? This is 1, 2, 3, 4, 5. 5 carbon is pentane, but this will be called cyclopentane. The last one that you see is 1, 2, 3, 4, 5, 6. 6 carbon atoms is called usually hexane. So in this case, because it is cyclic, it will be called cyclohexane. Sounds good? And you would see in their molecular formula, what is the molecular formula for this? Propane, this is C3H22456, C3H6. So what is the general formula for cycloalkanes? It is going to be CnH2n. Okay, so cycloalkanes basically consist 2 hydrogen less than their normal alkane counterpart. Okay, so for instance, if you were to write propane, normal propane would be C3H, it would be 8, C3H8 if it was propane, but cyclopropane is C3H6, so it has 2 less hydrogen than its normal straight chain structure. Okay, and when we draw something like this, this is essentially called a carbon chain. Okay, so this is a straight chain of carbon atoms. So sometimes you might hear people say this is a straight chain molecule, this is a ring structure. That's what the chain essentially means here. Chain means just carbon atoms attached to each other. Okay, those are cycloalkanes. Let's see if you guys can name these. Give the IUPAC name for each of the following compounds. Part A is, we simply see all single bonds here, which means this is an alkane. How many carbon? 1, 2, 3, 4, 5, 6, 7, 8. 8 is oct, so this will be octane. How about the part B? Alright, so this is a cyclic alkane. We know this has all single bonds, so we start counting 1, 2, 3, 4, 5. 5 is pentane, so this will be cyclopentane. Okay, now let's try to name these alkanes. The first one that we see is, again, it's an alkane. First, the question is telling you. Second, you also see there are all single bonds. How many carbon is this? 1, 2, 3, 4. 4 carbon is bute, and it's an alkane, so followed by ane. This is 1, 2, 3 carbon, so this would be, it's a cyclic structure, so it is cyclopropane because it's an alkane. Part C, we see how many carbons? 1, 2, 3, 4, 5, 6, 7, 8. 8 carbon is oct, and all of those are single bonds, meaning this is octane. And then finally we have D, 1, 2, 3, 4, 5, 6. This is 6 carbons. All of those are single bonds, which means this is alkane. 6 is hex, ane, and this is cyclic, so it would be cyclohexane. Perfect. Now let's talk about another concept which you will very commonly see in organic chemistry, which is called isomers. Structural isomers. Okay, what are isomers? Structural isomers, by definition, they have the same molecular formula with a different arrangement of atoms. What does that mean? Let's try to name these. Look at these two structures. Okay, what is this structure called? The first structure, this is 1, 2, 3, 4 carbon atoms, right? 4 carbon atoms will be called butane. This is how many carbon atoms? This is also 4 carbon atoms, 1, 2, 3, 4. But you will see in this case the number, the way these carbon atoms are bonded to each other is completely different. Okay, this is not simply butane, this is called isobutane. Okay, or you will also see another form, I'll show you. This can also be called as 2-methylpropane. And how did I get to this name? I'll show you that, but basically this has a completely different name from the above structure. But now let's see what are their molecular formula. What is the molecular formula for this? Carbon atom is 1, 2, 3, 4, 4 carbon atoms. Number of hydrogen atom here is 3, 4, 5, 6, 7, 8, 9, 10. C4H10. How about this? This is also 1, 2, 3, 4. Number of carbon atom is 4. Number of hydrogen atom here is 3, 3, 6, plus 3, 9, plus 1, 10. So you see their molecular formula is C4H10. But these compounds have completely different structural formula. They don't look the same when you look at their structure. And you would also see that their naming is completely different. They don't have the same names. And you would also see that because they have different order in which the atoms are arranged, they will behave differently chemically. So they have different chemical properties as well. So these type of molecules which have the same molecular formula but a different arrangement of atom or a different structure are called structural isomers. Okay, how can you differentiate them? You would see that they have same formula, but their names would be different or their structure would be different. Okay, what is important? They have to have the same number of carbon atoms and same number of hydrogen atoms. Okay, whenever you see something like this which is joined to each other in a straight chain, these molecules are called straight chain molecules. For instance, if I were to draw the line angle formula for this, it would be 1, 2, 3, 4. It's a very straight chain. I did not have to lift my pen up while drawing this structure. Whereas if I were to draw this particular structure at the bottom, how would you draw the line structure formula for this? It is going to be 1 carbon, 2 carbon, 3 carbon, right? And then this carbon that you see right here is attached to the carbon number 2. So in this case, the line formula for this particular molecule is going to be something like this, where this is not a straight chain now. In order to draw this structure, I had to lift my pen up. I had to draw a branch. Therefore, this structure is called a branch chain. So this is the straight chain in here, and we had to draw this particular line up separately, which means this is a branch out of the straight chain. Right? So such structures are called branched chain, wherever you have to basically lift your pen up while you're drawing the structure. Alright. So for instance, a simple question can be, can you draw 3 possible structural isomers of pentane? Pentane is, formula is given to you, C5H12. Structural formulas, what does it mean by structural formula? They have to have different arrangement of atoms, right? So one could be simplest. The simplest structure could be a straight chain, 5 carbons. So we start from 1, carbon number 1. I go 2, 3, 4, 5. So this is 1, 2, 3, 4, 5, 5 carbons. That is C5H12. How else can I draw this? I could draw a 4 carbon atoms in straight chain. So for instance, I could draw 1, 2, 3, 4. This is 4 carbon atom. The 5th carbon atom I could draw right here. That would be a branch structure now. How else can I draw this? I could draw it like this. I could draw, instead of drawing 4 carbons, I would draw 3 carbons in a straight chain, and the other 2 carbons I can draw like this. 2 different branches. So these are 3 structural isomers for this particular compound. 5 carbons, but they have different structural formula. So for instance, like this straight chain, this is a straight chain formula. This is a branch chain which has only 1 branch. This is also a branch chain which has 2 branches. Okay. Alright, so next we'll talk about alkanes with substituents. Okay, so right now we saw how to name these compounds. These are straight chain alkanes, so we know how to name them. The name for this is butane. Easy. But how do you name something like this? These are called alkanes with substituents. Substituents means whenever there are a group of atoms that are present as a branch or a side group, they are called substituents. Okay, how do you know it's a substituent? You basically, when you're looking at alkane, you're looking for the longest straight chain. So in this case, what is the straight chain? This is carbon 1, 2, 3, 4. 4 carbon, all straight chain. But if you go here, what is the straight chain here? This is carbon 1, 2, 3. And then to have this carbon right here, I need to lift my pen, so I have to draw a branch. So the straight chain, only straight chain that I have here is these 3 carbons. Okay, or you could have it like this. I could draw this as a straight chain, right? If I have this molecule, I could say this is my straight chain, which is carbon 1, 2, 3. I could also say that my straight chain is this right here. This is also 3 carbon straight chain. This is 1, 2, 3, and this is my branch. It really doesn't matter how you're looking at the molecule, right? As long as it is a straight chain, meaning you're not lifting your pen while you're counting these carbon atoms, that is a straight chain. and whatever is outside of this straight chain is a substituent. Okay, for instance, in this case, this is my straight chain, so this carbon right here is my substituent. Whatever is the side group attached to, or a branch that is attached to your long chain, that is called a substituent. Okay, now these substituents can be a carbon. For instance, in this molecule you see the substituent is also a carbon. It could be other groups, right? It could be halogens. Halogen means it could be fluorine, chlorine, bromine, iodine, any of these. Okay, if these are your substituents, how do you name them? Their IUPAC name is basically named as fluoro, chloro, bromo, or iodo. So if halogen is a substituent, they are named as fluoro, chloro, bromo, or iodo. If the substituent is a carbon chain, is a group of carbon atom, it can be 1 carbon atom, 2 carbon atom, 3 carbon atom. If the substituent is a carbon, it is called as alkyl group. Okay, all these terminologies are very important. It is called alkyl group, YL. So how do you name them? You basically name them with ending with YL. And what is the prefix? Prefix stays the same. If it is 1 carbon, prefix was meth. So what would be the alkyl group be called? Alkyl will be called as methyl. It ends with YL. Prefix followed by YL. So whenever your substituent is carbon atom, a group of carbon atoms or 1 carbon atom, it doesn't matter. It is called an alkyl group. Okay. For instance, if my substituent, let's say, is 2 carbons, it will be called ethyl. You can see them right here. This is methyl group. This is 1 carbon substituent. If the substituent is 2 carbons, it will be called ethyl. If the substituent is 3 carbons, it will be called propyl. If the substituent is 4 carbons, 1, 2, 3, 4, it will be called butyl. Similarly, you can have pentyl, hexyl. Okay, so basically what is the important part? It's called the alkyl chain or alkyl group, and the name has to end with YL. Okay, if it is halogens, F will be called fluoro, chlorine will be called chloro, bromine will be called bromo, iodine will be called iodo. Okay, now if this propyl group means this is 3 carbon chain, if this 3 carbon is attached like this, meaning it is attached from a corner carbon atom, it is called propyl. If these 3 carbons, instead of attaching from the corner carbon atom, it is attached from the center carbon atom, it will be called isopropyl, meaning this is now a branch. So what does that mean? Let's say if I have this particular long chain, I attach a propyl group like this. This is 1, don't end the show. This is 1, 2, 3. So if this is my long chain, this is my long chain, right? This is my long straight chain. What is my branch? This is my branch. What is the branch? This branch has carbon number 1, carbon number 2, and carbon number 3. So this is what branch? This would be called propyl. This alkyl group will now be called propyl. If it is attached from the corner carbon, then it is called propyl. If at the same time I could draw it like this, from here, let's say I draw it like this. What is my substituent now? My substituent is this group, which is also how many carbon? 1, 2, 3 carbons. But what is the problem here? This is attached from a middle carbon. It is a branched alkyl group. So whenever it's branched, it is called iso. So instead of being called 3 carbon propyl, this will be called isopropyl.
So propyl is,
For instance, if this butyl, if it is 4 carbon substituent and it's a straight chain, it will be called butyl. But if it is in itself, if it's a chain, this is also what? How many carbons? This is also 1, 2, 3, 4 carbons. But it has a chain within itself, it will be called isobutyl. Okay. Now let's see how would you actually name these compounds. So again, IUPAC has certain rules when you're naming such compounds that have substituents. First thing, you should be able to recognize that there is a substituent. How would you see that? Let's see. This has one carbon right here. Then I have another carbon, 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 carbon. All carbons have single bonds, first thing, right? Which means, what is this? This is an alkane. First thing I identify is, this is alkane. Next thing I see is, are all the atoms that are attached to these carbon hydrogens? No. Most of them are hydrogen, but I do have this chlorine and this second group, which is CH3. So these are the substituents. How do I know these are substituents? You will start numbering your carbons. Okay? You want to have the longest straight chain. The first aim, whenever you're naming a compound, is find the longest straight chain of carbon. Carbon atoms. That's your first step. What do I mean by that? For instance, let's say I start from here. This is my one carbon. This is carbon number 2, 3, 4, 5. These are all in straight chains, right? So how many total carbons I have? If I go like this, 5 carbons. If now I go like this is also a carbon, right? You have to adjust your eyes or train your eyes to see each of the carbon as a part of a chain sometimes. Okay, so for instance, I can start numbering from here. This is 1, 2, 3, 4. I can draw a straight chain like this. This is also a straight chain. I did not lift my pen. Only thing I did is I took a turn. That's it. Okay, but this is 4 carbons. This was 5 carbons. So this is still my longest chain, right? Another thing I can do is I can start numbering from here, which is 1, 2, 3, 4, 5. This is also 5 carbon. Let me redraw this in another color. So if I start numbering from here, this is 1, carbon number 1, carbon number 2. Okay, let me erase these. This will get very confusing. This is 1, this is 2, this is 3, and this is 4. How many carbon is this? 1, 2, 3, 4. This is also 4 carbon chain, which means this is also small. The longest chain possible here is 5 carbons. Okay, so now you can simply erase everything else. Which one is your longest chain now? You know, it is this straight line right here. This is my longest chain. This chain is called as longest chain, or it is called as the parent chain. Why parent chain? Parent chain means because this is what will give the actual name to your compound. Okay, so the longest chain is called as parent chain. Now we have to name our parent molecule. So what is our parent molecule? It is how many carbons? 1, 2, 3, 4, 5 carbons. So what is the name of the parent molecule? It is an alkane with 5 carbons, meaning it is pentane, right? Perfect. So now I have name of my parent chain. But this, if I draw pentane, if you write pentane, I would not draw this molecule. I would not draw chlorine, I would not draw CH3. So this is not the name of the compound. You need to tell me there is a chlorine, there is a carbon. But where is the chlorine, where is the carbon? How do I name that? You start numbering these carbons. Okay? How do you number these carbons? You're going to number the carbons so that your substituent get the smallest number possible. What does that mean? If let's say I start from here. I say this is carbon number 1. This is 2. This is 3. This is 4. This is 5. Okay? Pentane means I have 5 carbon. 1, 2, 3, 4, 5. Now I am saying on carbon number 2 I have a chlorine, and on carbon number 3 I have a, what is this group called? This is a substituent. What is the substituent called when it is Cl? Chloro. What is the substituent called when it is 1 carbon? Methyl. Right? Okay, now I need to tell where is the chloro, where is the methyl. So I can say, if I number these carbons like this, I can say that the chloro is on carbon number 2 and the methyl group is on carbon number 3. Okay, now somebody might say that, okay, you named it like this. What if I start numbering my carbons from this side? If I say this is 1, this is 2, this is 3, this is 4 and this is 5, right? Then my chloro is on 4 and my methyl is on 3. What is the rule? The rule tells you, you number the carbons so that all substituents get the smallest number possible. Okay, so which one would be smallest number? If I start from the left side, my carbon number is 2. If I start from the numbering from the right side, my carbon, the smallest carbon number I'm getting is 3. So which is the smaller number? From the left. Which means I should start numbering from the left side and not from the right side, which means these numbers that I wrote are not going to work for me. The numbers that will actually work for me are right here. This has to be carbon number 1, 2, 3, 4, 5. Okay, now you start naming your substituents. So my parent chain was pentane. How do you write the substituent? You would write the first substituent on carbon number 2 has a chloro, carbon number 3 has methyl. Which one comes first? It comes by alphabetical order, not by number of carbon atoms. So by alphabetical order. Chloro starts with C, methyl starts with M. So now by alphabetical order, it would be chloro. So we start with chloro. Where is it located? Carbon number 2. So you first put the number. Then you put a dash between a number and an alphabet. So this will be 2-chloro. Whenever there is an alphabet and a number, you put a dash in between. Okay. Now, 2-chloro. Where is the methyl? Dash 3-methyl. Pentane. So that would be the name for this compound. So the next rule essentially is you write the substituents in alphabetical order. And these rules, I'll keep on adding to these rules as we try more examples. Okay. So for instance, now if I give you this name and I ask you, can you draw the structure of this molecule? Let's draw the structure. Let's confirm if we actually wrote the correct name or not. Did we forget anything? So always when the name is given to you and you're writing the structure, remember, start from the end. Don't start from 2-chloro. Start from the end. What is the end? End is telling me it's a pentane. Pentane means it is 5 carbon alkane. So I'll start with alkane. I'll first draw my pentane. 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. Right? Now I'll number these carbons. My choice. I just drew it. I can number from wherever I want. So I start 1, 2, 3, 4, 5. These are my 5 carbons. Now you go for the next number. Next is 3-methyl. So on the third carbon, I'll draw a methyl group, which is, I can just simply draw a single chain. That means this is a methyl group, or you could write CH3. But if you're drawing a line structure, you don't put carbon, so you simply draw a line. Then I come here, which is 2-chloro, so I draw chlorine on second carbon. So now you can see, does this and this above look the same? Yes. That means your name is correct. Let me draw it here again. So this is 1, 2, 3, 4, 5. So this is 1, 2, 3, 4, 5. This is the carbon number 3. So third one has a methyl group and second one has a chlorine atom. So if you're drawing a line structure, it would look like this. If you were drawing an expanded structure, it would look like this. Okay, and usually you don't give these numbers in a structure. This is just for you guys to write, so you can practice how to write the formulas. Okay, so the rule is always find the longest chain first, then you put the number of carbon so that your substituent get the smallest number, and then you write this name of the substituents with the number of carbon atom in an alphabetical order. Okay. All these rules are also listed in the slides in case you forget. So find the longest chain, then you put the substituents, number of carbon atoms from the end nearer a substituent, meaning the substituent gets the smallest number. Give the location and name of each substituent in alphabetical order, and always put dashes, and there are no spaces within this name, remember that. Okay, whenever you're writing an organic compound, there are usually no spaces. Okay, it's basically dashes or commas. We'll see where do you need commas. Okay, let's try this. This is a cycloalkane with substituent. How would we name this? So whenever you have a cycloalkane, your cyclic structure gets the preference. Okay, your cyclic structure is usually regarded as your parent chain. When you look at this structure, how would you name this? I would say, okay, this is all, first thing I identify is this, what type of hydrocarbon is this? This is a cycloalkane. It is an alkane because it's all one carbon, single bond between all carbon atoms. It is a cyclic structure, so it is a cycloalkane. So what is the name of my parent chain here? My parent chain is basically going to be this particular chain right here. Okay, always your cyclic alkane is your parent chain. Okay, so for instance, in this case, how many carbons do I have? 1, 2, 3, 4, 5, 6. So 6 carbon means it is hexane. This is a cyclic structure, so this is actually cyclohexane. This is name of my parent chain. Now I need to name the substituent. If this is my parent chain, this molecule right here is my substituent. Now for substituent, first thing we see, this is a alkyl substituent because this is carbon chains. How many carbon does this have? 2. What is the prefix for 2? Eth. And what is the alkyl chain called? It would be called ethyl. Okay, so where is this ethyl located now? This ethyl, how would I start numbering my cycloalkane? Your substituent should always get the smallest number possible. So if I start numbering from right here, this would be 1. And I can't go smaller than that, right? I could do 1, 2, 3, 4, 5, 6. So my actual structure would be 1 ethyl cyclohexane. Okay, but there is a catch here. Most of the times whenever you see a 1 written, for instance in this case, if instead of giving you 1 right here, if I just gave you the name ethyl cyclohexane, you would still draw the same structure. Okay, so most of the times if your substituent is present on carbon number 1, you simply don't write the number. Okay, because that automatically tells me that you're telling me this particular alkyl group is present on carbon number 1. So the actual name for this compound would be ethyl cyclohexane. If no number is given, you can simply assume it is on, the substituent is attached to carbon number 1. Alright, so if your substituent is usually on carbon 1, we usually can skip the number 1. Let's try to name these particular alkanes. So the first alkane A, we can see in order to name it, first thing we identify what type of hydrocarbon this is. So when we look at it, this is all carbons have single bonds with each other, which means this is an alkane. Also, the question tells you this is an alkane. So to name the alkane, you basically write the name of the parent chain. So for that, we need to identify which is the longest chain. Here we can see the longest, there's only one straight chain right here. So we can start numbering from here. This is 1, 2, 3, 4, and 5. So this is a straight chain of 5 carbon atoms, which means this is called pentane. That would be name of our parent chain. And what do we see here as a substituent? We see a substituent of chloro. Now what is important here? Now we need to identify where exactly is this chloro located, which carbon number is it located. Now we can start numbering from any corner. Remember, you could start numbering carbon atoms from any corner carbon atom. It has to be a terminal carbon atom. You can start numbering from here. I could also start numbering from right here because this is also a corner carbon atom. So if I number from here, this would give me 1, 2, 3, 4, and 5. Okay. You cannot start numbering from in between. You can't just simply go right here and say this is carbon number 1. It has to be a terminal carbon. It can be any corner carbon atom. So now if we start numbering, if we are numbering from the left side, our substituent here is getting a number of 4. Whereas if I label and start numbering from the right side, my substituent gets a number of 2, which is again definitely a smaller number. So in this case, our actual numbering would be starting from the right side. So this, whatever we have in yellow, is not correct. Our actual numbering should start with the what we had before. So this would be 1. That means my chloro now is 2 chloro, since it's on carbon number 2. So name would be 2 chloropentane. And there is no space between any of these alphabets. Only we use dashes whenever you see something like, whenever it's a number and alphabet, in between number and alphabet, we put a dash. Now let's try to number or name our this second structure, which is B. So in case of B, let's see, here you kind of have to train your eyes. Okay, you could start, don't just jump into the structure and be like, okay, this is my parent chain. It might be correct for this question, but for other questions that might not be the case. So the ideal way is that you start numbering from each corner carbon atom and try to go in every single direction and check what is the longest chain that you can possibly get for this particular structure. Okay, so for instance, let's say I start from here. This is carbon 1, this is 2, 3, 4, 5. So this gives me a carbon chain of 5 carbon atoms. I can start numbering from other direction. I can go like this, 1, 2, I can go down here instead of going up. That would give me 3 carbon atoms, which is definitely small. I could go the other way. I could start here, say this 1, 2, 3. Instead of going down, I could go up. That would give me 4. So this is 4 carbon atoms, which is definitely again less than 5. So none of these are correct. Right now, my only answer that I have is this 5 carbon chain. I could also try, this is when I start from this corner. I could start from this corner. I could do 1, 2, go here, 3, and 4. That's again 4 carbon, so it is not the longest chain right now. I could do 1, 2, 3, 4. That's also 4 carbons. That is also not the best possible approach. I could do 1, 2, 3, and 4. That's also 4 carbons. So what I'm trying to show you here is that you could go from any, you could start from any corner and go till the any corner carbon atom. You just have to figure out which one gives you the longest carbon chain. Okay, I could start from this end. That would give me 1, 2, 3, 4. That's 4. 1, 2, 3, 4, 5. That is also 5 carbon atoms. Okay, so I could go like this. I could start from here, which is 1, 2, it's getting very messy right here, 3, 4, and 5. This is also 5 carbon atom. If I go like this, that also gives me 5 carbon atoms. What's important is that this is also giving you 5, this direction is also giving you 5, so you could choose whichever one you want. It would really not matter. Okay, and we'll try naming both of those compounds. Okay, so now let's try to figure out what are the numbers that are the best for us to use. All of these that we tried were less than 5, so we are going to stick with the numbering that we wrote first in yellow. So we'll stick with this, which was 1, 2, 3, 4 and 5. So that is a total of 5 carbon atoms. Now if this is my longest chain, I've identified that this is my longest chain. What are my substituents? Anything that is outside of this is a substituent. So this right here is a substituent. This is also outside of the carbon chain, so this is also a substituent. So how do we name this? The naming is the same rule. You first name your parent chain. Here my parent chain has 5 carbon atoms, so this is going to be pentane, followed by in the beginning, in prefixes, I basically am going to write the name of the substituent. What is the substituent that I have here? This is methyl group. This is 1 carbon. How many? Don't count this carbon in. Why? Because you have already counted, this is carbon number 3 of your parent chain. So if you have already counted this carbon in your parent chain, you cannot count this carbon in your substituent. This substituent only has 1 corner, so it has only 1 carbon. So this would be methyl group. This would also be, this is also 1 carbon, which means this is also methyl group. Where is this methyl located? This is on carbon number 2. This is on carbon number 3. Okay, so if this is carbon 3 and carbon 2, both of those are methyl. The rule is you cannot write 2-methyl, 3-methyl pentane. You're repeating the methyl group here. So instead of writing 2-methyl and 3-methyl, we will simply write this as 2, 3 dash dimethyl pentane. What this di means that you have 2 methyl groups on carbon number 2 and 3. So basically, if you have repeating substituents, you could add another prefix. So depending on the number of substituents that are repeating. So number of repeating substituents, you could use the following prefix. Okay, for instance, if it is repeating 2 times, the prefix would be di. If it is repeating 3 times, the prefix would be tri. If it is repeating 4 times, the prefix would be tetra. If it is repeating 5 times, the prefix would be penta. So basically you could keep on going, just like 6 would be hexa, 7 would be hepta. So this is also based on the same principle of the number of carbon atoms. Okay, only difference here is instead of meth, eth, prop, you basically are using these prefixes. Okay, so don't confuse these prefixes with the ones that we saw before. Okay, those are for number of carbon atom. This is the number of repeating substituents. If it is 2 times di, 3 times tri, 4 times tetra. Okay, so in this case this would be 2,3 dimethyl pentane. Now another important thing is, in this case I did not start numbering from here. Why? Because if I start numbering, somebody would be like, okay, this is the same structure. What if I start numbering from here? This is also 5 carbons. This is 1, 2, 3, 4 and 5. This is also the longest chain, right? This is also 5 carbons like above. But now I want to start numbering from the right side. Why not? Because if you number from right side, your smallest number that a substituent is going to get is 3, right? Whereas in this case, your substituent, if you start numbering from the right side, your substituent gets a number of 2. Which is the smallest one? 2 is smallest. So this is not the correct way of numbering your compound. Let's try to make some questions up ourselves and try to practice the rules that we just saw. And if there are any more rules, I'll tell you as we go through more examples. So let's say if we have this particular structure, have this, how would you name this particular structure? So if this is the given structure, again we see first thing we identify is that this is an alkane. It is all carbons here have a single bond. So first thing we identify, this is which type of hydrocarbon? Alkane. Now we know for naming the alkane, the rule is we need to find the longest chain. So you can start numbering from wherever you want. I'll start from here. Let's say 1, 2, 3, 4, 5. So this is giving me 5 carbon atoms in this chain. Let's try other direction. I can go 1, 2, 3. Instead of going down, I can go up. This gives me 4 carbon, which again is a smaller chain. I could go the next way, which would be, let's say 1, 2, again this is 3, and this I come down right here, that would give me this as 4. But this again is shorter chain, this is only 4 carbons. So I've already tried from this corner. I can now start trying from this particular corner. Let's start numbering that way then. So if I start from here, that would give me 1, 2, I could go down 3 and 4, right? Let's draw the structure a little bit bigger right here so that it's easier for you guys to see if I put all the numbers in. So I've already numbered these, right? And the longest chain I saw was the green one. Let's start numbering from this side. I do 1, 2, 3. Let's make this long, and I could go 4. That gives me only 4 carbons. I could also go the other way, where I could go 1, 2, 3, and then instead of going up, I could go down. This also gives me only 4. So this is still a smaller number. I could go 1, 2, 3, 4, 5. That also gives me 5 carbon atoms. So how am I getting 5 carbon atoms? Now the longest chain that's possible for me is 5 carbon atoms. Let's try to see where exactly are those 5 carbon atoms. Either this chain or if I go that way. So I'm going to delete rest of the numbering that we just did, which doesn't make sense, and I deleted the structure while doing that. So let me redraw this whole thing again quickly. The numbering that we did before was in this form. Oh my god, why are you doing this? So we go this, and then we had group right here and a group right here. So this was our structure, and the initial numbering that gave us actually 5 carbon atoms was 1, 2, 3, 4, and 5. Now I have 2 choices. Either I could go this structure on the left side, or I could go the parent chain as the structure on the right side. So this is also 5 carbon atoms, this is also 5 carbon atoms. Which one should I choose? The left or right? Should I start numbering from here or from the right side? I would start numbering from the left side. Why is that? Because that gives me a substituent number as 2, whereas the first substituent on this chain is at number 3. So out of 2 and 3, I'm going to choose 2 because that's the smaller number that a substituent can get here. So basically, this structure is not correct. This numbering is not correct. I would go with this. So now we name our compound. We figured out this was alkane. How many longest chain has how many carbons? 5. So this would be pentane. Now we need to name the substituent. So where are the substituents? I have a substituent right here. This is called bromo. Where is it located? It is on carbon 2. Then I have this substituent, which is a methyl group. Where is it located? On carbon 3. and a substituent right here. This is also methyl, which is located on carbon number 3. So now what do I have? I have a bromo and methyl. Which one will I put first? I go by alphabetical order, which is bromo and methyl. So B comes first. So we'll start with 2 bromo, and we have 2 methyl groups on 3. So how do we name those? If you have duplicates, that's going to be 3, 3 dimethyl pentane. Okay, we already had the name pentane written out beforehand. Now remember that rule is that whenever you're naming them alphabetical order, you go by name of the substituent. So in this case, the name here starts with bromo and methyl. This alphabet that you see di, this is not counted towards the alphabetical order. Not counted or not considered towards alphabetical order. Alphabetical order is based on the name of the substituent and not the prefix. This is just a prefix di. It doesn't matter if there is di or if it isn't. The way I wrote this is because there is a B right here and M right here, not because of the D. Okay, so remember that. All right, let's then try another question. Whenever you need to pause the video and just kind of like read through any of this part, you could always pause the video, rewind the video, or just pause the video, take a minute, understand everything in this question, and then move to the next question. Okay, so the next question, let's say we draw this. So if this is our molecule, I will draw, let's say, a Cl right here, and I draw this right here. So how would we name this particular compound? So we, again, first thing we see is that this is a hydrocarbon, which is all single bond, which means this is alkane. So the rule for naming alkane is we go by the longest chain. So let me start from here. 1, 2, 3, 4. I could go up 5, 6. That gives me total 6 carbon atoms. Next, I could go, instead of going up, I could go down. I go 1, this is still 2, this is 3, this is 4, 5, 6 carbon atoms. So in both of these cases, I'm getting 6 carbon atoms as the maximum number of carbon atoms. So I could go either way, it doesn't matter, right? The other way, the next possible approach is I could start numbering from here. If I start numbering from here, this is 1, 2, 3. I could go here 4 and 5, which is less than 6, so not my answer. Or I could go from here 1, 2, 3, 4, 5, 6, which is also 6 carbon. So I do have this option as well. I could start numbering from this side. I could start numbering from, let's try numbering from this last particular carbon. If I put this as 1, 2, 3, 4, 5, 6, this would also work. This is also giving me 6 carbon atoms. So now I have 3 choices where I can get 6 carbon atoms in my longest chain. One is if I go in this, but from left to right. Another one is if I go from left to right going up. Then I could go from right to left going down. Okay, which one should I choose? I should not choose this one where I'm going from right to left. Why? Because here the smallest number my substituent is going to get is 1, 2, 3. The smallest number my substituent will get is 3. Whereas if I go from left towards right, my substituent will get 1, 2. 2 would be my smallest number for this particular one. So basically we are going to number our substituent from this to that. Okay, let me repeat this if it is getting very confusing. Let's just remove all the other chains. So we want to keep the yellow ones and we want to keep the purple one. So let me get rid of everything else and let's rewatch this. Actually, let's just now redo this thing so we know where are our two long chains that we are getting. Let's number them again. So I'm getting one from here, 1, 2, 3, 4, 5, 6, right? Or instead of going this way, I could go 5, 6. It does not matter. As long as you have 6 carbon atoms, it would not matter. The other direction that I could go is from here, 1, 2, 3, 4, 5, and 6. Out of these two options, I want to go with the green option. Why? Because the first substituent on the green option that I'm seeing would lie on number 2, whereas the first substituent that I see with my purple would lie on carbon number 3. So the smaller number is 2, which means I'm going to stick with 2 and delete this particular numbering, as it will not work. It's not the best parent chain numbering for me. And I also deleted the molecule. So this was our molecule, right? Now let's start naming them. So we know our parent chain is what here? The parent chain is 6 carbons, which is hexane. So our parent chain is going to be hexane. And we have substituents right here, 2. One is this, another one is this right here. This substituent is called chloro. Which chloro? This is on carbon 2, so this is 2-chloro. And this substituent is how many carbon atom? It has 1 and 2. So since this is 2 carbon atoms, this is going to be ethyl, and this is on carbon 4, so this will be 4-ethyl. Why did we not count this particular carbon in? Remember, the substituent, you don't count the number which is the carbon which is part of the long chain. This carbon right here on carbon 4, we have already counted this carbon in our long chain, so we will not count this towards our alkyl chain. Our alkyl chain will only be carbon number this and this, and we will not count this particular carbon into our alkyl chain. So now which one comes first? We have chloro and ethyl. Remember, the numbering doesn't matter, the alphabetical order matters. So chloro comes first, so it will be 2-chloro, 4-ethyl hexane. No spaces, so ethyl hexane. That would be name of this particular compound. Let's try one more question. I will make a modification to this particular last question that we just did. Let's try one more quick question. So okay, let's see how would we name this particular compound. So again, we see it's all single bonds, meaning this is alkane. So we'll start numbering. Find our longest chain. So this is 1, 2. Usually we always, whenever we look at a straight chain in the middle, our mind just tells us this is the long chain. But never make that mistake. You should always confirm, even though it looks like the long chain. You should always do this step. Do not try to skip this particular step. Okay. So this would give me 6 carbon atoms. Okay. I could, instead of going down, I could go up. I could go 1, 2, 3, 4, 5, 6, 7. So now we can see here that if I go up, that gives me 7 carbon chain, which means the bottom chain is 6 carbon, which is not our longest chain. So our longest chain now is this particular chain, right? This particular chain right here. Even though it looks a little unorganized and not the conventional way, but this is the longest chain, and our substituents are going to be right underneath. Okay, but again, we should also confirm the other ways. Okay, so I've already gone both the ways from here. I can start numbering from this side. This would give me 1, 2, 3, 4, 5, and 6. This is also not my longest chain. I could go from here 1, 2, 3, 4, 5, 6, 7. This is also my longest chain, 7 carbon atoms. So this completes both the ways I can go from here. Let's go reverse from this side. 1, 2, 3, 4, 5, 6. This only gives me 6 carbon. So basically we have two options, which is giving us 7, which is either the option number in blue or the option in yellow. Okay, so I can get rid of everything else. So we want to keep the yellow and blue. I want to keep the yellow. Okay, so my options are now two. Either I go with this yellow or choice or with the blue choice. Now which one should I choose? We look for substituents. Where are the substituents located? On this structure I see two substituents. One is this, another one is this. If I start numbering from here, my substituent will get a smaller number of 2. But if I start numbering from here, my substituent will get 1, 2, 3, 4. The smallest number possible is 4. So which option should I choose? I should start numbering from the left side, which means I can get rid of the yellow choice as well. That is not the best choice for me. The best choice was the blue one. Okay, so now we can start naming our compound. Our compound will now be, longest chain is how many carbon? 7 carbon. So 7 carbon means this is heptane. It's an alkane, so it is heptane. What are my substituents? I have one substituent right here, which is chloro. The number for this is 2-chloro. And then I have another substituent, which is 1 carbon, 2 carbon. Again, we don't count this carbon because it's already counted in the long chain or the parent chain. So now this is 2 carbon, which means this is ethyl. Where is it located? On 4th carbon. So what would be my name? I start with chloro first because this is starting from C. So alphabetically this comes first. So our answer would be 2-chloro 4-ethyl heptane. No spaces. So heptane. Okay, so what is important here, you need to remember that you need to count and give it a try. It's a hit and trial approach. Okay, you need to give numbering a try from all the corners and see whichever one gives you the best longest chain. Again, I am doing this because I'm trying to explain you. I'm writing these numbers down and I'm explaining to you each and every approach. When you are actually doing this, you don't have to rewrite everything. You can just do this simply in your head. But what is important, don't skip this step. Try to number them all in all the directions and see which one gives you the best numbering for your structure. Okay, so let's say if I have this particular molecule, how would we name that? So in this case, we have a cyclic structure. It is alkane because it's all single bonds. So whenever you have a cyclic structure, that would become, you would give preference to your cyclic structure. That would become your parent chain. Okay. Now this in between this cycle is my parent chain. How many carbon is it? 1, 2, 3, 4, 5, 6. So 6 carbon means my parent chain is cyclohexane. Now I need to name the substituents, which would be right here. 1, 2, 3. I have 3 substituents. How many carbons are on each substituent? 1. So all of them are methyl. But I need to first figure out what are the numbers for these methyl, right? So for methyl, where do I start numbering? Can I start from here, up top? I shouldn't. If I start from here, I could go left or right? I could go 1, 2, 3, 4. I could go 1, 2, 3, 4. The number that I'm getting for my first substituent is 2. Whereas if I start numbering from right, this carbon, that would give me this as 1, this would be 2, this would be 3, this would be 4, this is 5, and this is 6. Then my smallest number on the substituent would be 1. So I want to start numbering from 1. So now your numbers are going to be 1, 3, and 5. So it would be 1, 3, 5 dash. How many methyl do we have? 3 methyl. The prefix was tri. So it will be trimethyl cyclohexane. Let's try another one. What if I give you this? Yeah, you have a question? So let's say if this is what I have, I'll draw this right here, and I will draw right here. How would we name this particular structure? Okay, so now if you start numbering this question, start naming this particular molecule, we could start numbering again, and we know in our numbering that this cyclic structure is going to be our parent chain, right? So now I know how many carbon is it? 1, 2, 3, 4, 5, 6 carbon. So this is also cyclohexane, that I know. Now we need to give the name to our substituents. So what are my substituents? I have this substituent and I have this substituent. This is methyl. This is 1 carbon and 2 carbon. So this is ethyl. Now we need to give them numbers. Where do I start numbering? I have 2 substituents on this cyclohexane. I could start my numbering from here. I know I need to give the substituent the smallest number, which means it has to be 1. But should I give this number ethyl 1 or should I make methyl 1? When you have a substituent like this and you don't know where should your numbering start, you go in alphabetical order. Whichever one is alphabetically, whichever one comes first will get the smallest number possible. So alphabetically I have ethyl and methyl. Who comes first? Ethyl. So ethyl has to get the smallest number possible. So this would be 1 right here. Then either I could go clockwise or I could go counterclockwise. Okay, meaning I could start here from 1. I could do 1, 2, 3, 4, 5, 6. Or I could also go 1, I could go here 2, 3, 4, 5, 6. Which of these are correct? I should go in the clockwise direction, because when I go clockwise I get substituent number as 1 and as 3, whereas if I go counterclockwise I get 1 and 5. So my correct alphabetical and numbering order is going to be the green one again. So I'm going to stick to this. So now if you name it, it will be 1, again alphabetical order, 1 ethyl, 3 methyl cyclohexane. So that is the final name of this particular compound. Okay, So let's try this question. So now we have already practiced a bunch. If the structure is given to you, how do you write the name? Now let's practice if the name is given to you, how do you write the structure? That is fairly simple. Okay, that you always remember, you should always start from the end of the name. Okay, never start from the beginning. So this is telling you it is 3-bromo 1-chlorobutane. So start from the end. The end tells you it is butane. But means 4 carbons and ane means single bond. It's an alkane. So let's start with the line structure. It needs both condense and line. We'll start with line. So I'll draw but first. 4 carbons, 1, 2, 3, 4. Each corner is 1 carbon atom. This is my butane. It tells me I need bromo and chloro. I can number from wherever I want. I am making the structure. It doesn't matter right now. Okay. So I'll name this 1, 2, 3, 4. Where is the bromo? I have 3 bromo. So this has bromo and 1 has chloro. So this would be Cl. That would be my final line structure for this particular molecule. Now if for some reason you would say like, okay, I want to start numbering from right here on the right side, that would be okay. 1, 2, 3, 4. Where is the bromo? Bromo is on 3rd carbon. Where is the chloro? Chloro is on 1st carbon. So this molecule and this molecule is exactly same. You know now. Why? Because when you start numbering, it really doesn't matter. Okay, as long as your name is coming out to be same, you have the same structure. Only thing that we have done in between the structure is we just bent the molecule slightly, and from here we just rotated the molecule and it gave us the structure. So drawing the chloro, you could draw it. Okay, you could, if you were to draw this chloro like this. This is bromo. You could draw Cl like this. You could draw Cl up above. You could draw Cl on the side. It really doesn't matter. Because this is, as long as it's not a carbon, the corner doesn't count. Because we only count if you leave a corner empty, we'll count it as carbon. Okay, so going from name to structure is fairly easy. Always start from the very corner. Okay. Now talk about some of the properties of these hydrocarbons. So hydrocarbons, especially alkanes, they basically have very different chemical properties. Some of these properties according to solubility and density. Okay, so most of these alkanes, basically we saw methane, ethane, propane, butane. Have you guys ever heard of these gases before? Some of these. Methane is the natural gas. Butane, used for camping, right? We get butane tanks. Propane, we use it for like, it also comes as a tank, propane tank for when we're doing grilling and stuff, right? So those things usually use these gases. So alkanes, whenever with carbon 1 through 4, most of these alkanes are gases at room temperature. Between carbon 1 through 4, the alkanes are gases at room temperature. And they are used, what is their purpose? They are used as the heating fuels. Alkanes with carbon 5 through 8 are very volatile liquids. They are liquids. As you increase the number of carbon atoms, they turn into liquid at room temperature. They are also used as fuel. For example, pentane, hexane, heptane, octane. They're usually used in industries and stuff. Okay. Alkanes, which is carbon 9 through 17, these are also liquids and they are found in, for instance, again they are liquids, so they are also found in fuels like motor oil, mineral oil, kerosene, diesel, jet fuel. Again, these are all used in as in industries as a fuel. Okay. Then we have some alkanes. As you increase the number of carbon atom, which is 18 or above than that, it becomes solid. These alkanes will turn into solid as we increase their temperature. As we increase their number of carbon atoms. At room temperature, they will turn into solids. Some of those solid examples are paraffin, which is like wax, which is used in as a coating on fruits and vegetables. Okay, so one of those examples would be paraffin. Other examples, for instance, we use Vaseline or petroleum jelly. That is also an example of an hydrocarbon which is semi-solid. It is carbon number 25 or more. Okay, so most of the alkanes you would see, they act as fuels, and most of them are 4 carbon is gases. Anything between those is liquid, between 4 and 17, and when it comes to 18 and above, it basically turns into a solid material. Okay, and how about solubility? Are these alkanes soluble or not? They are highly non-soluble in water. When we talk about solubility and we don't say any solvent, we are usually talking about in water. Okay, alkanes are very non-polar. Why? Because they only consist of these bonds, which is carbon carbon carbon, hydrogen carbon hydrogen carbon hydrogen. So these bonds cancel each other's polarity, or they are completely non-polar bonds. So they become very non-polar, which means they will not interact with water. They are not soluble in water, and they are less dense than water, which means if you have oil spills, right, gas spills or petrol spills, what happens? It's usually floating on water, which means they are lighter than water, so they are less dense than water, and they are again very flammable. How do we know that? Butane, methane, hexane, though you put any kind of bring fire next to it, it's going to just catch fire right away. Okay, all right, so those are properties of these alkanes. Now let's look at one of the reactions for alkanes. One reaction of alkane is combustion. We saw what is a combustion reaction before. A combustion reaction is when something reacts with oxygen and it burns, right? That was a definition of combustion reaction. So combustion reaction means it will react with oxygen to produce carbon dioxide and water. So what would happen? Alkanes consist of what? They have carbon-carbon single bonds. When you burn them in presence of oxygen, these carbon-carbon bonds are going to break and they are going to turn into CO2 and water, and lot of energy is going to be released. That's exactly how our gas works, right? Our stove top. You have methane gas coming out, we spark a little bit of light into it, and what happens? In presence of oxygen, it basically catches fire and it starts combusting, and it produces CO2 and water as a byproduct, and a lot of heat energy is released, which we use for cooking. Okay, where is this water? We usually don't see this water, right? When you turn on gas, you don't see water. It doesn't start raining suddenly. Why? Because the temperature is so high, it's releasing so much heat that water instantly vaporizes. Okay, so it basically turns into gas. That's why you don't see water as a liquid here, it is gas. So now the question is, I can give you any alkane and I'll ask you what are the products for this particular reaction when it combusts. As long as you see there is a hydrocarbon and in presence of oxygen, it is always going to produce CO2 and water along with energy. Okay, only important thing for you is you should know how to balance this chemical reaction. Let's try this question. Let's assume the reaction is not given to you here, and I ask you what will be the product when you burn or combust C4H10. What are the combustion products of C4H10? C4H10, you don't need to know what it is. As long as it's a hydrocarbon in oxygen, it is going to produce CO2 and water, and it will release a bunch of energy. Now your only process is to balance this chemical reaction. So how many carbons do we have here? 4, which means we have to have 4 carbons on the right side, so I add a 4 right here. Now how many hydrogens do I have? Hydrogen is 10 on the left side, so we need 10 hydrogens on the right side. How can I make it 10? It's already 2 times 5 will give me 10, so I put a coefficient of 5 in front of water. Okay, remember oxygen is always left for last. Why? Because you see it's common to both these products. We always leave the common stuff for the end. Now we can balance our oxygen. How many oxygen do we have in total? This is 4 times 2, give you 8, and this is 5. 8 plus 5 will give you total of 13 oxygen. This is an odd number. How can I make this equal now? I need total 13 oxygen. So what can I do? This is already 2. I can write 13 over 2 right here. Right now I can, in a step. I have not finalized my reaction, but I can write 13 over 2 for now. Now in order to get rid of this times 2, divided by 2, I will multiply the whole reaction by 2. Okay, if I multiply the whole reaction by 2, what would that give me? That would give me 2 times C4H10, which is right here, plus 13 over 2 times 2, which would give me 13 oxygen atoms, or molecules, sorry. Then I have 2 times 4, which would give me 8 carbon dioxide. Then we have 2 times 5, water, which would give me 10 water molecules, plus energy. So that is how you can balance your overall reaction. So the simple question would be, what would be the combustion product of this particular reaction? Or I can simply just give you this, C4H10 in oxygen. Can you complete this particular reaction? So you should know this is a combustion reaction. It will always produce oxygen and water along with some energy. All alkanes give this reaction. All hydrocarbons essentially give this reaction.